Okay, let's start today's lecture. Yesterday we have learned about the properties of Laplace transform, and in the properties of Laplace transform we learned about the linearity property, scaling property, time shifting property, and frequency shifting property, along with time differentiation and frequency differentiation property. So if you want to review this, so in the linearity property, we have the Fourier transform of the time functions scaled as the time function scaled, and they are sum up to have the equivalent function in the Laplace domain. So the scaling property is in fact is f of at is 1 over a f s over a. So it means that if there is an expansion in time domain, so there is contraction in Laplace domain and vice versa. So for the time shifting property, we use the exponential e minus as, and for the frequency shifting property, if we have the exponential e minus at, so we have the f of s plus a. And the time differentiation property is we have the s f of s with the initial condition. So if we have the second derivative, so we will add the first derivative in the Laplace domain with the initial condition. So similarly, the third derivative, we can have this, and so on, we can take the nth derivative in time domain. Also, we can have the integral in time domain. So the integral in time domain is in fact is 1 by s f of s, and the frequency differentiation is t f of t is minus t by ds f of s. And also the frequency integration is in fact is f of t divided by is the frequency differentiation property. So the periodicity is in fact is written in this form, f1 of s divided by 1 minus st. Also we can find the initial value and the final value of f of t with the help of f of s. So how can we find the initial value and final value? For initial value, we have s f of s and s approaches to infinity. For initial value, the s approaches to infinity, and for the infinity value, s approaches to 0. So with the help of this, we can find the initial value and the final value of the function in time domain. Also for the convolution, we have the multiplication in Laplace domain. So these are the properties which we can use for the application of Laplace transform in circuit analysis. So today we start the application of Laplace transform for the circuit element models, and we analyze different circuit and their transfer functions. So today we will study the circuit element models and some of the circuit analysis techniques which we have used in frequency domain and time domain. So the circuit analysis technique like mesh analysis, nodal analysis, source transformation method, Thevenin method, and other methods are also used in Laplace transform circuit analysis techniques. So for this, we have the steps, and these steps are almost the same which we have studied in the frequency domain transform, or the phasor representation of the circuit. So first transform the circuit in S domain, and then we apply the circuit analysis techniques, and then we take the inverse transform to find the time domain solution of our analysis. So we have the voltage current relationship in time domain. So this is the Ohm's law, and that can be represented in Laplace domain by V of S is equal to Ri of S. So we can find the voltage across the resistor in the Laplace domain by this method. Also, by dividing R with the voltage across it, we can have the current I of S. So we can transform this relationship in Laplace domain and back to time domain with the help of the same relationship. So this is the resistive element of the circuit. What about the inductive element? So for inductor, we know that the inductor voltage is in fact is the rate of change of current across it. So its value depends on the initial condition of the inductor. So for example, we have the time differentiation property df of dt is equal to sf of s minus f of 0 negative. And f of 0 negative is the initial condition, the time just before 0. What will be the value of current across the inductor, right? So this can be represented in Laplace domain, that voltage is transformed into V of S, and the value of inductance into the value of di by dt. So di by dt is its Laplace transform is Si of S minus the initial condition. So we can have V of S is equal to S Li of S minus Li 0 negative. So if we have to find the value of the current, so we can also find the value of current from this equation. So for this, we first divide it by inductance, and we will get the value of this relationship, and then we move this initial current value at the other side. So we will have V of S L plus initial value of the current. And now we find the value of I of S by dividing V of S by small s L into I, initial value of the current, divided by S. So in fact, this current is represented in fact with an inductor and a current source. So actually, in fact, this inductor is behaving as a current source due to the initial energy stored in across the inductor. So for this, we have this current source, and this current source is due to the initial value of the current. So in frequency domain, we cannot take into account the initial value of the current, or we consider it 0. So, but here we can take into account the initial condition, initial value of the current stored across the inductor. Right? So if we see the voltage, so the voltage representation is this, that we have the inductor and we have the that much voltage is appear as a voltage source across the along with the inductor. So the voltage is, there is some additional voltage because of this because this initial value of the current. So you can understand that we can have the voltage across the inductor in this form, and we can have the current across the inductor is divided across these two elements, right? So what about the capacitive element? So the current passing through the capacitor is C dVc by dt, or we can say that the current I is equal to CV. But in case of the time varying voltage, we have to take the derivative of the voltage, because we have to take into account the rate of change of the voltage across the capacitor, so we can find the value of the current. So again, we apply the time differentiation property, and by this time differentiation property, dVt by dt, that term will be SV of S minus V0 negative. So the current I is SCV of S minus CV0 negative. So this CV0 negative is in fact is the current source in parallel to the capacitor, and that is the current I of S. And when we calculate the value of V of S from this equation, so we will have this much capacitance and a voltage source in series with this capacitance. So this is in fact is the representation of the circuit elements in Laplace domain. Now we see the applications. Sorry. So for example, there we have a capacitor and there is an initial voltage V naught across it. So this is the initial charge stored across the capacitor, and this capacitor is discharged through this resistor. And when this capacitor is discharged through this resistor, so the current I will pass through this resistor and the voltage V will be appear across it. So when we have the initial voltage across it, so we replace the series voltage source with the capacitance 1 by SC in Laplace domain. So we have the current I of S passing through this resistor, right? And the voltage V appears across it. Now we solve this circuit as an example. So first we apply the mesh analysis, because there is only a single mesh. So what will be the voltage? The voltage source V naught by S is equal to 1 by SC into I plus RI. right? So it is almost the same we apply for we apply in the phasor domain. So the impedance is R plus 1 by SC into I is equal to the V naught by S. So from this we calculate the value of I, which is CV naught RCS plus 1, right? So we can also rewrite this in the form V naught by R S plus 1 by RC. Now see, here this relationship again. So we have analyzed this relationship again. So this V naught by R is in fact is the uh, gain, and this 1 by RC is in fact is the pole, right? And if we want to express this relationship with in time domain, so we can take this value of V naught by R constant and 1 over S plus A, 1 over S plus A, and this A is in fact E minus AT by UT. That is the exponential decaying function. That is the E minus AT U of t is the exponential decaying function, and the value of A is 1 by RC. So we substitute the value of A is equal to 1 by RC. So that is exponential is E minus t by RC U of t. And when we want to calculate the voltage across the resistor, so the voltage across the resistor is Ri, and we multiply with the value of R. So that is V naught E minus t by RC U of t. So in fact, what is important here that we have taken in account the initial voltage across the capacitor, and we have calculated the value in time domain. So previously in frequency domain representation, we have no consideration of the initial conditions of the capacitor, and we assume it as 0. Also, if we have the complex voltage source with the varying value of frequency, so we can also calculate this relationship. So if we have to find the value of the current, across the resistor, or we have to find the value of the voltage across the resistor, so we can also replace this initial voltage with the current source. So we can have the parallel representation of the circuit. So this CV naught is in fact is the current source, which is in parallel with the capacitance 1 by SC into R. Now we have the this much current is divided across this branch and this branch. So CV by naught, CV naught is in fact is the current V by R into V divided by 1 by SC, or that is SCV. So from this we can calculate the value of voltage across the resistor. So that value, because the voltage across the resistor is almost the same. We have the voltage across the capacitor. So that voltage is V naught S plus 1 by RC. And also we apply the inverse Laplace transform to have this relationship V naught E minus T by RC U of T. And 1 by RC is tau, is the time constant of the circuit. So time constant, the value of the time constant is depends on the value of resistance and capacitance, and that value is equal to tau is equal to RC. The value of tau is equal to RC. So also we know that the value of tau is equal to 1 by omega p, the inverse of the pole frequency. So because the pole frequency is 1 by RC and the value of tau is equal to RC. So first, the circuit analysis, we consider the zero initial conditions, and with zero initial conditions, we have the voltage across the resistor is V of T, and the current passing through it is I of T, and that is represented in the Laplace domain as. Also for inductor, if we consider zero initial condition, so this is represented by SL. And with zero initial condition, the value of capacitance is in fact is C is equal to 1 by SC. So the time domain and S domain representation of passive elements under zero initial conditions are shown in this figure. So I hope it's almost the same as we done in the frequency domain. So the only thing is that J omega is represented by S here. So we analyze the circuit to find the voltage V out of T across this inductance of 1 Henry. So first I need to transform this circuit in Laplace domain. So for the Laplace domain, we have U of T. This U of T is 1 by S. This 1 Henry is SL, and the value of L is 1 Henry. So it is S, and 1 by SC is equal to C is 1 by 3. So that is 3 by S. So you can see here that U of T is 1 by S. This 1 Henry is S. We transform it S. And this 1 Henry is, this 1 by 3 farad is equal to 3 by S, and we replace it by 3 by S. Now we apply the mesh analysis for mesh I1 of S and mesh I2 of S. So for mesh 1, we have the relationship 1 by S is the voltage which is dissipated across 1 plus 3 by S I1, 1 plus 3 by S I1 of S minus 3 by S I2 of S. So 3 by S I2 of S. For mesh 2, we have 0 is equal to minus 3 by S I1 plus S plus 5 plus 3 by S I2. So how can we do this? Because this minus, this is 3 by S is minus I1 of S. For second mesh, we write it, and we have 5 plus S plus 3 by S into I2 of S. So we write this. Now we find the value of I1 from mesh 2. So we get this value of I1. And we substitute this value of I1 in equation 1. So we will get this new equation. And by solving this, we find the value of I2 of S. This value of I2 of S will help us to find the value, find the voltage across the inductor. And that value is SI naught, V naught of S, SI naught. So this is SI2. I naught is equal to I2. So we substitute this value in this relationship. Now we have cancelled the higher order term of S in the denominator with this value of S. So we will get S square 8S plus 18. And we transform this relationship in the form of E minus AT sine omega t. So that for sine omega t, we have omega S square plus omega square. And if the function E minus AT f of t, so we have the omega S plus A square plus omega square. So we transform the relationship in this form. And in this form, we have the value of under root 2 S plus 4 square plus under root 2 square. So it is 3 by 2 E minus 4t. Why? Because the value of A is 4. So it is E minus AT or will be E minus 4t. And sine omega is under root 2. So we have under root 2t, that much voltage across the inductor. So it's very difficult to solve if we don't have the Laplace transform method. Now we consider the circuit with initial values. So we have to find the voltage across the capacitor, assuming that the initial voltage across the capacitor is 5 volt. So now we have to consider the initial value of the capacitor as well. So what I can do is that we can have a voltage source in series with the capacitor, or we have a current source in parallel with the capacitor to represent this initial condition. Rest of the function remains, rest of the process remains same. So we take the Laplace transform. So the Laplace transform, we have this value of I of t is C dV by dt, and this I of s is SCV of s minus CV 0 negative. So CV 0 negative is the value of the current source appear in parallel across the capacitor. So V0 negative is 5 volt and the value of capacitance is 0.1 farad. So CV0 negative is 0.1 into 5 is 0.5 ampere. So this 0.5 ampere current source appears in parallel with the capacitor. So the capacitance value of 0.1 farad is 1 by SC or 10 by S. So also this 10 and this 10 are same here, and this 10 E minus T U of T. So it is in fact is E minus AT is 1 over S plus A. So if the value of A is 1, so it is 1 over S plus 1. So when it is multiplied by 10, so we have 10 divided by S plus 1. Sorry. So we have 2 delta of T. So that value of 2 delta of T is in fact is 2 ampere, because delta of T is 1 in last domain. So it is 2 ampere, right? So we can solve this, we have converted this circuit in the Laplace domain. Now we have the voltage V naught of S appear across this node. So this V naught of S appears across this node. So only this current is entering into the node. This current is entering into the node, and 0.5 ampere current is entering to the node, and all three currents are these two currents are leaving the node, and this current is also entering the node. So this current and this current and this current are entering into the node, and we find the value of this. So at this point we have V naught of S. So 10 S plus 1 minus V naught divided by 10 is the current entering, plus 2 this 2 and 0.5 is current is entering, and then we have V naught by 10 is leaving, and V naught by 10 by S is also leaving. So we can solve this equation for V naught, and we have find the value of V naught from this relationship. So this is in fact is 10 S plus 1 plus 25 is equal to V naught S plus 2, and V naught is given by this relationship. Now you know that we cannot take the inverse Laplace transform until or unless we can separate the denominator terms. So this can be separated by partial fraction, A over S plus 1, B over S plus 2. So we can take the, apply the, inverse Laplace transform for this. So we substitute the value of S is equal to -1 to find the value of A. So this value is 10, and we have the value of B. When we substitute the value of S is equal to -2, and that value is 15. So that value of V naught of S, that fraction is solved is by 10 by S plus 1 and 15 plus 15 by S plus 2. So this is V naught of T is equal to 10 E minus T, because the value of A is equal to 1, plus 15 E minus 2T, which is because the value of A is 2, and both are decaying exponential, so that is U of T. So I want to express one thing here, that in case of RC circuits, in case of RC circuits, we have the decaying exponential. We have the decaying exponential because the value of A is multiplied with the U of t. Only the positive part from 0 to t will be considered. Here we have not considered the initial. Here we have considered the initial value of initial voltage of V naught across the capacitor. And in the next example here, this V out of t across the capacitor is also the decaying exponential. So
सर ये डिकेइंग ये एक्सपोनेंशियल की वजह से है?
Yes, because the U of t represents that this exponential is decaying, because the exponential is in fact is in this form. If you want to see it,
U of t तो सर वो स्टेप रिस्पॉन्स को शो करेगा ना, मतलब कि 0 से आगे.
So it is E minus AT. Right, as you have seen in the last lecture. So that is in fact is decaying for the, and that is rising for the negative part. For the negative part it is rising, and for the positive part it's decaying. So when we consider U of t, so it means that we are considering only the positive part, this part. So in fact, what is the value of this V out of t? This is the value of V out of t, right? And with this initial condition, so we have calculated the value of this V out of t with V naught of 0 is equal to 5 volt. So in all other techniques, we cannot solve this problem. We can solve this problem only by differential equation or by Laplace transform. Otherwise, it is difficult to solve this circuit. So we have used the Laplace transform method to eliminate the differential equation problem. So this is all about today's lecture, and later we have a discussion about the lecture.